Am I audible? Anyone please respond? CSC roll number 6. Okay, so let us recap the topic process synchronization. So what is the definition of process synchronization? As we discussed that a process synchronization is a task of coordinating the execution of process in a way that no two processes can have access to the same shared data and resources. For example, if we have a data item or variable X, which is shared by two programs P1 and P2, right? So the process synchronization says that we have to make sure that no two process or more than two process access this shared variable at the same time. Okay. Similarly, it happened in case of shared resources. For example, if it is a printer. Okay. So P1 and P2 cannot access printer at the same time to perform the printing operation. Okay. So this is all about process synchronization. Then we have our types of process. On the basis of synchronization. So we have discussed that we have two types of process. First one is the independent. Another one is the cooperating process, right? So if process are not interlinked or not dependency or do not share the critical section or shared variable or resources, those processes is called independent processes, while the other process which are sharing the shared variable or sharing the data or resources, we are saying those processes are the cooperating process. Or in other words, you can say that a process that can affect or be affected by other processes executing in the system. For example, if there is a P1 and it affects the P2, similarly P2 which affect the P1, then we can say that the two processes are the cooperating process, right? Now, next we have studied that why do we need a process synchronization, right? So please mute yourself. We have various regions for which we need a process synchronization. First, for the shared data, data must be consistent. Okay, so the first is the data consistency. Then preventing race condition. So we have already studied what is the race condition. I will also recap this one. So prevent race condition. Then we have, please mute yourself. Okay, then we have deadlock prevention. Okay. Next we have a priority control, means which process will be executed first. Then we have a concurrency control because modern day systems are concurrent systems. Next we have a critical section management. So this is the very important. So we have seen that let us suppose we have two process A and process B. Okay, process A writes on the shared data, whereas process B reads the shared data value. Okay, if we allow to perform the both operation at the same time, what will happen? There may be chances the data value is be changed and the incorrect value of data is read by the process B. So it is a data inconsistency. That's why we always make it so that at the same time, the shared variable or shared resource will be not accessed by any of the process. Okay. So what we have studied about the race condition, that we have already seen the motivating scenario where we have one value count equals to 5 and two process 0 and process 1 is trying to change the value. Process 0 basically increase the count value by 1 and process 1 decrease the count value by -1. Okay, so we have seen that when we are executing the micro instruction of the code, there may be chance of context switching, and for that we have three cases where the count value after execution of two codes may 5 or 6 or 4, right? So we have basically three values. So this is called race condition, where data inconsistency occurs due to the order of execution of instructions, right? Next we have seen that producer consumer problems, where producer produces an item and consumer consume the items It is a similar type of micro instruction which is run by process 0 and process 1. Okay, process 0 represents the producer, process 1 represents the consumer. The constraints are, we have to check overflow condition for a producer process, underflow condition for the consumer process, and accessing memory buffer at same time should not be allowed due to data inconsistency. And last one is the fixed size buffer. Okay, these are the 4 constraints which we use during the producer consumer synchronization problem. Okay, we have seen that we have 3 variables: in variables, out variables, and count variables. So in and out, these 2 variables are locally shared between producer. In is for producer, out is for consumer, and count is the global shared variable, means both producer and consumer will be access the count variables, right? Next, we have seen example of producer consumer. Okay. So now let us move to the next example, that is the printer spool problem. I think I have already teach this one. Let me check. प्रिंटर स्पूलर हो गया था क्या तुम लोगों का? Okay, we have already completed printer spooler problem, where the various printing instructions are shared using a spooler for a printer, right? Then we have seen different sections or elements of program. For example, in any program, we have an entry section that controls the entry into critical section. Then we have a critical section, of code or text, where the shared resources or variables are shared. Then we have a exit section, which basically handles the entry of other process that are waiting in the entry section. Then we have a reminder section. So in reminder section, all other parts of codes which is not in critical entry and exit section are known as reminder section, right? Then we have seen what is the critical section problem. That in critical section problem, basically we have to design a protocol, okay, which ensure that when one process is executing its critical section, no other process is allowed to execute critical section. Okay, now let's come to the requirement for solution of critical section. Solutions means to design a protocol. So a solution for critical section in operating system must meet the following three requirements. We have already discussed in the last class. First one is the mutual exclusion. In short, it is called ME. So in mutual exclusion, no two processes are present simultaneously inside the critical section at any time. That is, only one process can allowed to execute critical section at any time. Okay, so basically, why do we need a mutual exclusion? For safety purpose. Okay, you can say that for a safety, if no process executing critical section at the same time, so there will be no chance for the overwritten of data, right? That's why we need a mutual exclusion. The second important condition or properties of the solution or protocol, that progress. What is the meaning of progress? So we have a multiple definition or multiple properties. What it says, if no process is executing its critical section, then the selection of process for the critical section cannot be postponed indefinitely. So if what basically I am saying that, let us suppose this is the critical section. Okay, we have a two process P0 and P1, right? Right now there is no process in critical section initially or at any time. Now P0 wants to access critical section. Okay, this is the critical section for 0. This is the critical section for 1. Okay, having the shared data X. Okay, if P0 wants to access critical section, then P0 should be allowed. If P1 wants to access critical section, its own critical section, then P1 to be allowed. Okay, the only condition is that that if the process not executing their critical section, then any process want to execute its critical section, it should be allowed. So if no process is executing its critical section, then the selection of process for the critical section cannot be postponed indefinitely. Okay. So basically it ensures that prevention of deadlock. How? In the last class, we have seen that, let us suppose this is the railway track. Here train A and train B moves on the same railway track, right? So it will be stopped. Okay, so A is waiting for B, B is waiting for A. Okay, so it will be not accessing the critical section or move forwards to the destination. So basically in deadlock condition, no process execute its critical section. Okay, for the infinite time or indefinite time. Okay, so prevention of indefinite time to access critical section is known as progress. Okay, so in other terms, you can say that a process executing outside of its critical section cannot prevent other process for entering their critical section. For example, you can see here B wants to move. Okay, but A is stopping to B. Similarly, A wants to move, B is stopping. So a solution which satisfy the process synchronization must have a fulfill the properties that it should be progress. So a process executing outside of its critical section cannot prevent other process for entering their critical section. Processes attempting to enter critical section simultaneously must decide which process enters eventually, right? For example, let us suppose this is the critical section. P1 wants to execute this critical section, but P2 blocks the P1 to enter its critical section. This is not a progress condition. Okay, so no process will stop another process who wants to enter its critical section. It totally depends on the willingness of any process. Okay, now the third property is called bounded waiting. Bounded waiting in other terms also called no starvation. Some books written no starvation, but mostly we used bounded waiting, no starvation. Okay, so what it says, no process should have to wait forever to enter its critical section, right? Just like in SRTF, we have seen that there may be cause of starvation. Okay. Similarly, in bounded waiting, we have to make sure that no starvation condition occurs. Okay, so no process should have to wait forever to enter its critical section. There should be a bound on getting chance to enter its critical section, right? What is the meaning of bound here? So basically it says that after execution of some processes, the interested process will get the chance to enter its critical section. So for example, after the 100 processes, execution of their critical section, the process P1 will execute its critical section, right? Or you can say that, if I am elaborating, there is a limit to how many other processes are able to access their critical section before the requested process request is granted, right? So this is a bounded waiting, or you can say that, let me change the page. So if any solution or protocol is not following bounded waiting whenever there is a possibility of starvation. Right. These are the three conditions or three properties which we have to check for any protocol design or any solution for the process synchronization, right? Next, let us see what are the assumptions of solution for critical section. So, assumptions for solution of critical sections. So, there is no assumption about the hardware instructions and the speed of processors support, right? Next, basic machine language instruction executed automatically. Right, these are the two assumptions. Now, let us see the synchronization techniques. First, we have a software solution. Next, we have a hardware solution. Then OS support solution. Basically, it is a two types. One is called or you can say that using semaphore. OS supported the synchronization problem. So it is of two types. One is called binary semaphore. Another is called counted semaphore. Okay. Counting semaphore, counted noise. Then last one is the compiler supported solution. Okay. So what software solution is? It is a algorithms whose correctness do not depends on any other assumptions. Okay, so it is a pure software based solution for the synchronization. So what are those software solutions? The first is called algorithm 1 or strict alteration or its also name is the turn variable based solution or some book refers Baker's algorithm. Okay, so this is the solution number 1. Then we have a algo 2, use of leg variable. Then we have a algo 3, that is called Peterson's approach. Right, it is a combination of algo 1 plus algo 2, right? So all these algorithms 1, 2, 3 are basically based on two process solution. Okay, so they are applicable only for the two processes. Then we have a algorithm for the multiple process solution. Then we have a Bakery's algorithm. So these are the 5 types of software solutions, or there are many more. Okay, but in syllabus probably we have a algorithm 1, 2, 3. If we have enough time, then we can also look into the multiple process solution and Bakery's algorithm. Clear? So let us move to the solution or algorithm 1. We'll explain later what are the various hardware solutions. So basically it's two type basically we use, or three types you can say. One is the interrupt disable. Okay, second one is the test and set, and third one is the swap instructions or swap variables. OS supported, you have seen already that we have a semaphore. Okay, semaphore have two types of operation. One is used for the wait, another one is used for the signal. Right, it is two types. One is the binary semaphore. In binary semaphore, the value of semaphore is 0 or 1. Okay, so if value of semaphore is 1, it means that one process is accessing or executing its critical section. Other process should be wait. Okay, when value of semaphore is 0, it means there is no process in critical section. Okay, so any process willing to go into critical section, they can change the semaphore value to 1 and enters in critical section. Okay, then we have a second type is the counting semaphore. Counting semaphore, value of semaphore will be not restricted only 0, 1. It can be increased as per our requirement based on the number of processes. Whereas compiler support solution is nothing but a monitor solution, you can say. So in coming or later classes, we will also see the what are the drawbacks of the software solution, hardware solution, OS supported solution. Okay, so let us start the first algorithm, that is called strict alteration algorithm. So let me change the page. also called turn variable or decus. So what is the first condition? That the two processes are cooperating process and competing for their critical section, right? So in this algorithm, we have a single shared variable that is called turned. So it is a binary variable. It can take a value of either 0 or 1. Clear? So let us consider we have a two process P0, P1. Some book will take Pi, Pj, right? And turn value is I or j. If I am taking I and j, then value of turn equals to I and j. Okay. So let us P0 wants to execute if while is true. So it is a non-critical section codes. So we are interested from here. While I will explain it first. Let me write. Okay. So you can see that I have written some line of codes that if P1 will be P1 will wants to execute. So while 1 means one while is true. So we first execute a non-critical section of codes. Okay, we are not bothered about that. Now you can see here we are basically using turn variable for giving the turn to the process to access its critical section. For example, if turn value is 0, it means that process 0 will execute its critical section. If turn value is 1, process 1 executes its critical section, right? So you can see if initially let us suppose turn value equals to 0. Okay, clear? So turn value 0 means what? P0 will be executed first. You can try to check while turn not equals to 0. Turn not equals to 0. Is it correct statement? We have a turn equals to 0. So it is a false. Okay. Because value of turn is 0, not 1. So it is a false. So process 0 will execute its critical section to break the while loop. When it completes its execution, what it can do? It have to change the value of turn so that other process, that is the P1, if it wants to execute, it can able to execute. Okay. So it makes the turn value 1 and executing the remainder section. Okay. So this is how the code of P0 behaves. Similarly, we can write the code of P1. So it is a while if P1 wants to execute non-critical section while turn not equals to 1. Critical section, turn equals to 0, remainder section, so what it says, it is a entry section which controls the entry of process into its critical section. So we have a while loop here. Okay, if we broke this instruction in detail, you can see if I break what basically it says, while turn not equals to 0, do nothing, right? It is also called a BG waiting. What is the meaning of BG waiting? So BG waiting means CPU can execute this instruction while, okay, without doing any useful work. यहाँ हो क्या रहा है? Only loop ही तो execute हो रहा है. Okay, while are in loop. If while is true, do nothing. If while is true, do nothing. While is true, do nothing. If while is false, then the process come out from the BG waiting. Okay, so BG waiting is what? Wastage of CPU cycle. Because to execute this instruction, we need a CPU cycle, and in this execution, we are not performing any useful work. Basically, we use to block some other process. Let us see how. Similarly, this is what? Exit section. So exit section controls the process which are waiting for their critical section. You can see if I made a turn equals to 1, now P1 is qualified to enter its critical section. Otherwise, P1 will be wait. So here you can see turn variable indicates which process go to its critical section, right? For example, turn equals to 0. It allows inside the critical section. Similarly, turn equals to 1. ठीक है, right? So let us come to the main point, that properties which we discussed, mutual exclusion, progress, bounded waiting, will hold for this algorithm or not. So let us do the analysis. Mutual exclusion, progress, bounded waiting. We have another portability or architectural neutrality. Okay, for time being, you consider this one. So I will explain how the mutual exclusion is achieved. Progress is not achieved using this algorithm. Bounded waiting is achieved. Portability is achieved. Basically, what portability or architectural neutrality is, if we do not take a support from OS, okay, then it does not depend on the architecture of systems. That's why it is called architecture neutrality or portability. Means I can port this algorithm to any other system. Okay. So if there is any hardware support or software supports, then it depends on the architecture. So what I am saying, the algorithm one satisfy the first properties of mutual exclusion. It does not satisfy the progress. It also satisfy the bounded waiting and portability. In portability, there is no issue because it is a pure software solution. So there is no support of operating system needed. So come on to the first analysis, that is the for mutual exclusion. Okay, so let us take a 5-minute break or 7 minutes right now. It is a 10:26. So we'll meet on 10:32 or 10:35. It's okay. Okay. Okay, let us resume the class. So what I was talking there, we'll analysis the algorithm 1 for the mutual exclusion, right? So let us check whether a process is in critical section and other process is trying to enter its own critical section will success or not. Basically what I am saying, let us suppose a process is in its critical section and another process is trying to enter its own critical section. Okay, so if mutual exclusion will be achieved, then other process will not access its own critical section at that time when another process is executing its critical section, right? If mutual exclusion is violated, then other process is also able to enter its own critical section. Just like during race condition, we have seen that producer and consumer both are updating the same data variable, that is count. Okay, so if we achieve mutual exclusion using the algorithm 1, right? So there is no race condition. So let us check. So let us suppose initially, actually I have to, okay, let us write here. Initially, let us suppose turn variable is 0. Okay, because turn have only two options, either if value is 0 or 1. Turn 0 and process P0 wants to execute its critical section. Clear? So let us see what happened. It will execute its own code. So if I am naming this instruction 1, 2, 3, 4, 5, 6, so it will be help. So 1 will be executed, no issue. 2 will be executed, no issue. When we reach at 3, so it will be check whether the while condition is true or false. While true, false. Okay, so you can check turn equals to 0. Here, turn value not equals to 0. So it is a false condition. So it will break the while loop. अगर टर्न का वैल्यू 1 होता तो फिर ये क्या होता, करेक्ट होता, राइट? तो फिर P1 will be not enter inside the critical section. But here the turn value is 0 and we are checking the condition turn value not equals to 0 is true. It is a false statement, so while loop will break. Okay, if while loop is true, then what we will do? We will do nothing. We just execute the while loop at infinite time until unless the condition will dissatisfied. Okay, so false. So we broke the while condition. Then we enter its critical section. Execute 4. Okay, process P0 in its critical section. Now hold. We have to check that mutual exclusion is achieved or not for using this algorithm 1. So now P0 is in its critical section. Okay, here P1 also wants to enter its critical section, right? So what it will do? It will be execute its own 1, 2, 1, 2, 3, 4, 5, 6. Right? So 1 no issue, 2 no issue. When it reaches 3, we have a while condition, true or false. Right? So now it checks turn value not equals to 1. Yes, right now value of turn is what? 0. So 0 is not equals to 1. So it is a true condition. So it is a true. So what will you do? Infinite looping. So it will be execute this one. If it's true, do nothing. तब ये क्या होगा? यहाँ पे ही लूप हो जाएगा. Right? P1. So P1 cannot enter its critical section because P0 is already executing critical section and value of turn equals to 0. So for this condition, mutual exclusion is achieved. Now, what will happen then? After 4, it will be execute 5. When we execute the 5 instruction of P0, fifth instruction of P0, it makes the turn value equals to 1. Now, since turn not equals to 1 is a false statement, it's entered into the critical section. But at that time, P0 is already executed their critical section. Okay. So at the same time, no two processes are executing its own critical section. So mutual exclusion is achieved. Fifth, then sixth. Okay. Any issue? Similarly, the condition will change that initially P1 wants to execute. Okay. The third value equals to 1. And meanwhile, whenever the P1 inserts into the critical section, P0 also wants to execute. But due to turn variable value is 1, the while loop of P0 will not allow to execute P0 to execute its critical section. Okay. So at the same time, only P1 is executing its critical section and blocks P0 to enter its critical section. Right. So mutual exclusion is achieved. Clear? So this is how algorithm 1 satisfied the mutual exclusion criteria. Okay, no issue. Now we'll check progress. For progress. For your understanding, I am rewriting the same code in this page also. While any process P0 wants to execute, Okay. What progress says that if there is no process inside the critical section, if any process willing to go to its critical section, it should be allowed. Okay. Or in other words, we say that no other process can block to the process who are or which are willing to enter its critical section or their critical section. So since we are discussing about only two processes, so willing to enter its critical section, right? So let us assume initially turn equals to 0. Let us assume the value of turn equals to 0. So turn equals to 0 means what? Process P0 will allow to enter its critical section. P0 is allowed to enter its critical section. Now P0 turns the value of variable equals to 1, means execute this one. So this will allow is allowed to enter critical section. Okay, so what you can see that one process executing its critical section, then change the turn variable and ensure that other process can enter its critical section. So a strict alteration. P0 execute first, P1 execute, then P0, P1. If P1 execute first, then P0, P1, P0, like this one, P0, P1, P1, P0. Okay, so till there, yeah, two processes are willing to execute, no issue happen. But what happened if only one process want to enter into critical section and there is no willingness to the other process? What I am saying, let us suppose we have a turn variable equals to 0, right? P0 do not want to execute its critical section, but P1 wants to, better to use here, critical section, not willingness, and P1 wants to execute its critical section. So you can see here, since the value of turn is 0, P1 will be not execute. You can see here 1, 2, 3, 4, 5, 6. It execute 1, 2. At 3, it will goes to the infinite loop or BG waiting. So it will not enter into critical section due to what? Due to P0. Why? Because turn value is what? 0. If P0 will be executed, then the turn value will set to 1 and then P1 will be able to enter its critical section. In other terms, you can say that P0 blocks P1 to execute its critical section. But the definition of progress says that no process blocks the execution of other process to execute its critical section. So here it violates the progress. Means the algorithm 1 do not make sure the progress will achieved or not. Okay, so progress is not achieved due to the some algorithmic issue will rectify in the next algorithm how this problem will be solved. So till now, mutual exclusion achieved by the algorithm 1 solution. Progress is not achieved. Now comes into the third property, that is the bounded weighting. Bounded weighting, what says that if any process want to execute its critical section, the postponement of critical section execution is not happen indefinitely. Okay, there should be some time bound or some limits. So since it is a alternative, a strict alteration means if process 0 wants to execute, it can execute when turn value is 0. In case of turn value is 1, it have to wait till the process 1 will execute. Means only one process will be a limit for the algorithm 1. Okay. So if I am elaborating this one, case 1 you can consider, let's turn equals to 0 and P1 wants to enter its critical section, then at max P1 have to wait for only one process P0 to execute its critical section. So since here is no indefinite waiting, so we can say that in this case bounded waiting achieved. Now in case 2 is nothing but a vice versa, that turn equals to 1, P0 wants to execute into the critical section, P0 have to wait for only one process P1 to execute its critical section. So the algorithm 1 satisfied the bounded waiting properties. So we can say that ME achieved, progress not achieved, bounded waiting achieved, portability achieved. Portability is what? The solution provides portability as it is a pure software mechanism implemented at user mode. Okay. User mode implementation. Right? It does not need any special instruction from the operating system, that is no OS support. Clear? So let us solve a problem. So consider the given codes for the two processes P1, P2, while S1 equals to S2 critical section S1 equals to S2, and while S1 not equals to S2, critical section S2 equals to not S1. Assume S1 and S2 are two Boolean variables and initial value can be randomly chosen. Okay. Then, which of the following statement describes the properties achieved? Options are ME but no progress. B. Progress but no ME. Then we have a C. Neither ME nor progress. And D. Both ME and progress. Right. Problem is okay. We have a code given. We have to check that the given synchronization code will make sure that mutual exclusion occurred or not, or progress occurred or not. Let us solve. Let us suppose initially the value of S1 equals to S2 equals to 0. Okay. So place 1 that both have the same value. So exclude the P1. While S1 equals to S2 means if both the value is equal, P1 will be not allowed to enter its critical section. It's infinite loop due to S1 equals to S2. Then we will check P2 will execute or not. So P2, better to write down 1, 2, 3, 1, 2, 3. So P1 will be execute 1, so not executed. P2 will be execute while S1 not equals to S2. So of course P1, P2 will be executed the first code because while loop is the false. Since value of S1, S2 equals to 0, it will be executed critical section. Then value of S2, right now S1 equals to 0, S2 equals to 0, S2 equals to what? Not S1. Not S1 means reset to 1. Okay? Now let us check P1 will be executed or not. While S1 equals to S2, but for second time Let us try P1. 1. So since while statement true false, दोनों इक्वल है क्या? नहीं है, एक का वैल्यू 1 है, एक का वैल्यू 0 है, so false will be executed. Then critical section, then again make the value of S1 is what? Equals to S2. 1. Okay, so again P2 will be executed, P1 will be executed. Here strict alteration is achieved and no two process at the same time critical section. So we can say that the given codes or protocols achieve the mutual exclusion. Right. So what about progress? Let us check for the progress.
Yeah, about any meeting.
Okay. So you can consider another case, S1 not equals to S2. You can see that this code will be executed first, then this one. Okay. So I have also write this one. Case 2, S1 not equals to S2. Means if S1 equals to 0, S2 equals to 1, or if S1 equals to 1, S2 equals to 0. Any condition you can take. So first P1 will be executed, then P2 will be executed, then P1, P2. Here in this case, P2, P1, P2, P1. Right? So progress. Let us suppose the initial value of S1 equals to 0, S2 equals to 0. Okay. And P1 do not wants to execute its critical section. P2 willing to execute its critical section. Clear? P1 do not wants to execute critical section. P2 wants to execute its critical section. So for P2, when it execute the instruction 1 while true false, since value of S1 equals to S2 is what? Same. So while is true, so it will be in infinite loop. Since there is no process inside the critical section and P2 wants to enter its critical section, but it do not allow to enter its critical section. Why? Because the value of S1, S2 are the same, which will be due to P1. So what basically it represents that progress is violated or progress is not achieved in this case or given codes. So the option first will be true, mutual exclusive, but no progress, right? You can make another notes on the basis of some books. I have written this one, that the mutual exclusion and progress are the primary condition ME and progress for any solution to be accepted for the critical section, whereas secondary condition are bounded waiting and portability or architectural neutrality. Okay. So based on some textbook, I have written this statement. So this is all about the algorithm 1. Now, here problem is that with the single turn variable, that if no process want to execute its critical section, then other process also unable to execute its critical section. Okay, that's why in next solution, that is algorithm 2, we basically utilize the two variable solution, or not exactly a two variable solution. Instead of using a single variable, we use the flag variable or flag array. Okay, which helps that if there is no willingness of the process, then willingness of process will enter its critical section without depending on the other process, right? So let us see how we can use the flag variable. Flag variable, it is also called algo2. Some book also refers interested variable mechanism, right? The same statement that consider two processes are competing for their critical section, right? So instead of turn variable, here we have a flag variable. Flag 0 is used for P0, flag 1 is used for P1. So initially both is false. So let us see how we can write the code. So if P0 wants to execute while it's true, okay. So basically what's it do? It makes its flag true, right? So similarly, P1 wants to execute, it makes its own flag 1 is true, right? Now we have to entry section, which controls the process to enter its critical section. So I have to block P1 to enter its critical section when P0 is in its critical section, while flag 1 means, why I am writing this statement, if P0 checks whether P1 is its in critical section or not. So how it can check? It can check that flag is true or not, because flag represents that whenever the process initially both the flags are false, right? So whenever the process wants to enter or ready to enter its critical section, better to use ready to enter. So it will make the flag true, right? Then execute critical section. Since execution of critical section over, to make it false, so that other process can enter its critical section. Similarly, while flag 0 critical section, make it false, remainder section, right? So let us do the analysis part. So before starting, I will tell the algorithm will achieve mutual exclusion, progress, do not achieve the progress, bounded waiting, do not achieve the bounded waiting. So progress and bounded waiting basically not achieved due to deadlock. Okay, so we'll see how deadlock breaks the popularity of this algorithm, right? So first analysis is for ME. So initially we have considered that both the flag for flag 0 and flag 1 are false. Take a condition or case 1. Now in case 1, write the statement 1, 2, 3, 4, 5, 6. Consider P0 wants to execute its critical section. Right. So instruction 1 will be executed, 2 will be executed, and makes flag 0 equals to true. Right. False to true. It's okay. Now, when it's executing the third, it has true or false. Check flag 1. What is the value of flag 1? Here, flag 1 equals to what? False. Right. So, while loop breaks, so third will be executed. Then during fourth, okay. Now at fourth, let us try to make activate P1 activate. P1 activate for critical section. Okay. Right now check. 1 will be executed. 2 will be executed. While we are on 3, check. Flag 0. What is the value of flag 0? True. True means infinite loop means P1 will not be allowed to enter its critical section, right? So it will not disturb the execution of critical section of P0. So it will be easily execute the statement 5. The statement 5 says that flag 0 is false, means we make it the false 6 and then complete it, right? So mutual exclusion in case 1 is achieved. Let us see the case 2. Case 2 is the reverse of above scenario. means P1 wants to execute its critical section to 1, 2, 3. Okay, so there is no differences between the case 1 and case 2. But we have another special type of case 3. Okay, due to which progress and other properties do not achieve. So what I am saying that initially P0 wants to execute. When it's executes the instruction, suddenly P1 also wants to execute and context switching occurred. What I am saying that assume P0 wants to execute, right? So first is executing, second is executing. See here it makes the flag 0 equals to true. Now suddenly at 2, after execution of 2, context switching occurred. Right? And P1 wants to execute. Its critical section. What will happen? The P1 first instruction will be executed, then second it will make what? Flag 1 equals to true, right? So both the process makes the value of flag true at the same time, right? So now comes to the third statement, true, false. It will be check flag 0. Of course, flag 0 is true, so it will be in the loop. So P will be not executing its critical section. Now, context switching occurred and P0 wants to execute. So you can see here, already we are executing the second, we have completed the second execution. Now the third statement, true, false. It will be check flag 1, true. So since flag 1 is true, so it is a busy waiting or infinite loop. While loop will not break, it will execute the do nothing. Okay, so you can see in the both cases, we stuck in the entry section, right? So P1 wants completes its execution. P2 also wants to execute its critical section, but both are unable to enter its critical section. If I change any value, that is flag 0 or flag 1 to false, then one process is able to enter its critical section, right? So here you can see that there is no process in critical section. Okay. Also, the willingness of process to enter its critical sections are there, which means the progress do not achieved for the second algorithm. So violation of progress occurred in second algorithm. Why? Because here deadlock occurred. One process P1 waits for the process 0 to complete and make flag 0 false, and process P0 waits for the process 1 to make the flag value flag 1 to false. So deadlock occurs Why? P1 wait for P2 to make flag 1 to false. P2 wait for P1 to make flag 0 to be false. So due to deadlock, progress is violated. Actually, we have to find only one condition, at least one condition where the property is violate. Okay. So since this is a example of deadlock, okay, so bounded waiting is also not achieved. Better to write in next page. So bounded waiting, what bounded waiting says that there should be some limit, but in case of deadlock, if deadlock occurred, it means there is indefinite waiting, right, which violates bounded waiting also. So in this second algorithm or protocol, we achieved mutual exclusion, but progress not achieved, bounded waiting not achieved, portability achieved, deadlock achieved, which should be actually no deadlock, better to use. Okay. So this is all about the second algorithm. Right now it is 11:23. We'll meet at 11:30. Okay, for the third algorithm, that is called Peterson algorithm. At 11:30, I will take the attendance, so you can just communicate to your friends.